Thank you very much for the introduction. It's a pleasure and an honor to be on the campus of Waterloo University. This is the first time for me in this town, in this university. And this morning I had a number of talks with some of our faculty. I'm very impressed. I'm impressed by the quality of their work, impressed by the overlap, their interest with my research. And also impressed by the Center for Quantum Computing, which is, I think I visited very many places. This is probably the first one I briefly visited. They have an outstanding group of faculty work on quantum computing and quantum communication, which is new to me. And myself is that mostly related to nano research for last 25 years, 30 years or so. And I want to utilize the next hour or so to give you a talk about what we have been doing recently related to energy and related to sensors. So let me tell you what we have been doing for the last over a decade. Okay, we focus on a small scale energy. Particularly started 2004, we was looking for energy for mobile devices, for small sensors. And when I first started this work, that time was nobody cared about this. They don't think this is important, this is useless, okay? And I have a lot of story to tell you at the very beginning, okay? At the very beginning. As time progresses, I'll tell you this is the things we are very much interested today, particularly with the Internet of Things, with the sensor network. So we call small energy or nano energy. When I founded the journal called Nano Energy, even people ask me, what do you mean by nano energy? Do you mean a little tiny energy? Okay. By today, this has become a field. Okay. So when you do this smaller energy, then you say, what are the possible applications for that? You're looking for medical purposes. Implantable medical devices. You're looking for remote patient monitoring for healthcare. You also look for environmental protection because if you have water quality, infrastructure, this requires millions of billions around of sensors around the globe. How can you power these sensors? Okay, for example, you see our home have a number of these smoke detectors, sometimes little things. Sometimes we forgot to check. Is this working or not? Unless alarm one day, I say, oh, we need to change the battery. If you have a lot of things moving around, 90% of the Internet of Things, if you do not make it self-powered, will not be possible. This is Cisco study show the results. Also include many things, asset tracking and everything. So this is the world we are living today. We need a lot of sensors, a lot of things we need to know. How do we make this sensor powered? It's become a bottleneck technology. Nothing works without power. We know that, right? So this is our object for the research. So back to 2006, I published the first paper on the energy harvesting. I'll come back to that. A year later, I wrote this one, particularly called self-powered nanotechnology. That time was my dream. The dream was say, okay, we make a very little tiny medical devices and we can collect the data. Can we power this, send the data continuously without changing the battery? So this was a fiction that time, was with the blood vessel inside here, and then we have our nano sensor here. I say, is this possible? So there was a dreaming list back to then. But as a time progress now, we're slowly making this close to be possible. In some area, already possible. So this was, I wrote as a self-powered that time, and this phrase appears first time in my paper was 2006 in that paper for that. Let me show you this picture for that. When we finished the work, this was the instrument we used, okay? And a few people my students I work at that time. After we finished the work, we took a picture. We took a picture because I treat those guys with a simple lunch. That they finished the first paper. I said, okay, guys, done. Let's have a lunch. Okay. And on the table, I told them one sentence. I say, you folks will never forget today. I have two meanings. Number one meaning is that I felt this is something we can do for very many years, could be important, but it was just a vague feeling. The second thing I tell them, that day was Christmas Day. You guys work with me in a lab. You will never forget about this. Right? So, but we never thought. See, when we finished the work, it was around here. The output is only about 5 millivolts, almost useless. But as time progressed, we made a lot of enhancement. Over the course, we invented a number of new fields. For example, use piezoelectric for energy generation. Later on, use a trouble electric nanogenerator here. This will be the focus of my talk today. Later on, we have the idea called blue energy. I will also talk about this. Along the path, we also work on 2,6 compound semiconductor, use zinc oxide as example, introduce the field of Piezo Tronics and Piezo Tronics. And this is another field we coined during the course. So when we're searching for this one, we found something way more than we thought at the very beginning. But if you don't search, you find nothing. You have to search, okay? So this, let me start from here. What is the nanogenerator? First one, let's see the basic principle. If we have a piezoelectric material, piezoelectric have two kinds. One is piezoelectric domain-oriented. The second one is structure-oriented. This structure-oriented is for zinc oxide is a structure-oriented. This crystal has non-central symmetry. So that means what? The cathodes and anion centers are overlap. But once you apply mechanical force here, the cation and anion center polarize, give you a dipole moment. If this gives you one dipole moment, all these units add up, give you a macroscopic potential. And this potential is a polarization along the length of nanowires. That means that here we have polar charge, here we have another polar charge, and this is the driving force for the electron to flow. For example, if you see here, we have the polar charge, we drive field, the electron has to be driven to flow, and if you release the strain, the polar charge disappears, the electron flows back and forth. So this was when we first introduced that, use the piezoelectric effect to convert tiny mechanical energy into electricity. So this was the beginning. So when we show this one, let's say, oh, that time we put a single nanowire, a very little tiny nano, about 50 micron in the length, about half micron in diameter. Just put on the finger edge here so we can make it here. As you see, as the finger moves, we can generate an AC current as we saw, right? And later on, we put on use the heart beating of a small rat for power generation. And this was the starting of self-powered pacemaker work back to 2008. So this was the beginning. But today I'd like to talk to you first one from the fundamental theory of this power generation. Then we come to technology application and then other field. Okay, so this is the very basic idea. And what is the difference of this power generation from traditional power generation? Okay, traditional power generation is well established. Is Faraday invented electromagnetic induction 1831, and is one of the most important inventions in the history of science. And he was found that use the magnetic rod, cut through magnetic flux, there's a current flow through the rod. Okay, so this is using Lorentz force driving electron flow in a conduction rod, and this is called conduction current. So later on, this evolves, become the power generator we utilize today. Okay, What we observe for the piezoelectric factor, and later on, trouble electric fact, goes back to Maxwell's time. Okay, when Maxwell derived the Maxwell equation here, at the first did not have this term. This term was the displacement current. He proved that all these equations are not self-consistent unless you theoretically add up this term he called displacement current. That time is a virtual current. He said displacement current is not an electric current of moving charges, but a time-varying electric field. It's also due to the polarization of medium give you this. They have two terms. Displacement current have a time variation of electric field. This is the permittivity, and this is the medium polarization term. But this term has two components. One is the medium self. The second one is the surface charge. Normally, the surface charge being ignored. So if you look at the classical electrodynamic books, they don't have the surface term. But if you have a piezoelectric, you have the polar charge. You have a triboelectric, you have the polar charge, which come to play. And this is the current we observed in a piezoelectric nanogenerator. Now let's look at the theory a little more, okay? Let's say we have a piezoelectric material like that. We have an electrode. Then you apply mechanical strain, polar charge are created. Polar charge are created. This polar charge created, if you increase the magnitude of force applied, you have higher charge density, which have more current flow, and which is what you see experimentally over here, okay? Then, if you have this medium here, if this is isotropic medium, for simplicity, we have the displacement vector is the dielectric constant multiplied by the permittivity multiplied by the electric field. So the displacement current give you here. So this is what we started normally when we derive the electromagnetic wave. But if you have a piezoelectric materials, use the surface polar charge exists here, you have an additional term. And this term was missed in the literature because most people focus on electromagnetic wave rather than energy. If you include this term, this polar charge is related to the charge of the surface like this. So if you introduce this to the calculation, you find the displacement current is related to the straining rate, change rate of this system. So the current is a measure of the straining rate. That means how fast you strain these materials, you get the current. Normally, our work in the past is always start from the Ohm's law. Ohm's law derives the dynamics of this current transport. But here, this means what? This displacement current is the current go inside the medium. Outside is the conduction current or capacitive current. But the two meets at the electrode make a complete loop. So this is how the Maxwell's displacement current come into play, and which is a current normally we are not familiar with. Okay, so this is the piezoelectric current. Let me show you my major talk today. This was invented 2011, and first I show you what we invented. Then I go to the theory, explain to you for that. If you look at the left-hand side, this is the classical electromagnetic generator. And you have to have a gear transformer to make sure these things run fast. If this runs slow, it cannot lit up any lights because the output voltage is proportional frequency of the rotation. However, if you have our system here, this uses two medium contact sliding one against the other one. Suddenly, this many lights being lit up. You can see the difference. This is a higher voltage, lower current. High efficiency at a low frequency. This is a higher current, low voltage. High efficiency, a high frequency. Both are different. So let's look at this a little more. So what is going on here? So when you talk about the triboelectricity, people sounds very familiar, right? This very sound familiar. Let me tell you some background here. Tribology has been around for many, many years. I don't know how many they record in the literature, but I have this picture I took myself. If you go to my hometown, Xi'an, they have this Terracotta Warrior Dig from ground, which was made 250 years ago. So when I look at this one, then I find this, then you zoom in here, you find the shoes. Look at the shoes. This is the people made 2,200 years ago. They know tribology then. They know tribology then. They make the geometrical arrangement, everything here. Old phenomena. But very little usage for triboelectricity. If you look at the nature, we have the thunderstorm, and 1880 they have wished machines use the electrostatics and later on Van de Graaff generator. That's about it. So we always take this as a negative factor. Very fond use of that. They say, well, what the magic of this one? So if you use trouble electricity, it's very difficult, very complicated. It relates to the surface morphology, surface roughness, type of materials. But when we, in the middle school, the first class we study electricity is this. What is electricity? A glass tube, rub on the floor, get a static charge. We know that. Then after that is electric current. However, the question is, how does this charge generated? How does the charge from one material shift to the other one? And you can say, well, we use the complicated quantum calculation. But if my shoes is rubber and all this one, how do you do quantum mechanics calculate that? It's very difficult to calculate. So I'll offer you some new insight into this phenomenon. So it's an old phenomenon lacking of modern quantum mechanical interpretation. It's science, unresolved science. So let's look at this a little more. So what we do is that, let's do this one, use atomic force microscopy. This is the metal tip squatted on the surface of silicon. And then if you apply different bias to the tip, you can deliver positive charge or negative charge on the surfaces if you're rubbing this tip on top. So you can manipulate what kind of charge you deliver to the surface. This is the trouble electricity. The trouble electricity. Okay, then if it is a semiconductor, you can easily explain that. I'll come back to this one. But at least if you apply no bias, you can see this is the voltage you can the charge you deliver to the surface. So in such a case, there's trouble electricity. The question is, how does the charge transform from one side to the other side without coming back? Why do we have to be contacted, squeeze one against the other in order for the charge to be transferred? So we just have some publications I want to go through with you. 2 years ago, we made our trouble electric nanogenerator, as I showed you just a moment ago, that thing's rotating, and inside a tube, this box tube furnace, so we can control the temperature. So we measure the output of the trouble nanogenerator as a function of temperature. What we find, raise the temperature 273 Kelvin, roughly room temperature 293 Kelvin, to above to 533. So this is about 250 degrees C. You can see the trouble electricity drops dramatically. Okay, then this was a surprise. We thought this is kept there forever. We found it was very much temperature dependent, only around to about 300 to 400 degrees C. Recently we raised to 400 degrees C by this one. But if you measure at room temperature, it remains on for forever. Hours. But if you raise to, let's see, this is 150 or so, it decays with time. If you raise to 350 or so, to 400, this drops very quickly. With a few seconds, it's gone. So what this means that this is an electron emission process, thermal emission process. So we use the model, thermionic emission model, to model our data. We find that based on the electron thermionic emission equation, there's a potential barrier here. And the electron has to overcome this potential barrier in order to transfer from one place to the other. So we find this is electron transfer here, and it's also related to overcome a barrier at the interface. So through those studies, we find what? Let's look at the first case here. We have a metal and a semiconductor or dielectric case. Two are separated. And this is the distribution of electron inside around the Fermi level here, and this is given by the Fermi-Dirac distribution function here. If you bring the two metal and the dielectric in contact here, and then when the contact here, because the surface states here have a lower energy, the electron will transit from here to here. Electrostatic charge goes here. But now, if you separate the two, because those electrons are located lower than the Fermi level on this side, in order to go back, they have to overcome a barrier to go back, so they remain in the dielectric. So this becomes electrostatic charge. electrostatic charge. Then if you heat up to temperature, higher temperature, let's say from T1 to T2, the Fermi-Dirac, this tail goes up. So it means there's a possibility that this electron can hop out, KT, overcome the barrier, goes to the other side. So this is for metal semiconductor we can easily understand. However, in our life, we have everything have trouble-electric effect, like a wood, amorphous, glass, whatever. This model cannot explain that because none of this one have well-defined band structure as we draw here, surface state. No. So how do we understand that? So we came up with a model. The way that we can see contact electrification, there have to be contact. Why contact? This material had to be squeeze the other material. If you look at the atomic cell, that means one atom from belong to A materials has to push against the other B atom belong to B materials. If they separate part, this is the potential well. Okay, no electron transfer, because this is, in order for electron transfer, this have to overcome to get here, and distance is too far. They cannot do that. However, if you rubbing one material against the other one, squeeze, they have electron cloud overlap. Must be. If you have electron cloud overlap, if you look at the middle point here, this barrier compared to originally become lower. Then there's a chance for electron to move to here to here. So this electron jump to here will remain there to fill these states. If you separate the two materials, this transit charge will remain there, so make this negative charge, this is a positive charge. Okay, positive charge. Now if you heat up to higher temperature, if the KT is high enough, so for the electron have a thermal energy which can overcome the barrier height, can be thermal ionically emitted to vacuum or to the other material, then it disappears. So this is why when we heat up our things out to certain temperature, the trouble electricity gone. This we don't know before. We thought it's there forever. A very old problem. But still today, we are not fully understand about this. You think we have to do all kind of quantum mechanical calculation? Let's calculate this. Room temperature quantum mechanical phenomena. What happens in our daily life? So that means the old problem need new scientific explanation, and we are continuous to dig into this field to understand this one. Then you say, well, what it has to do with me? Let me show you. The invention of trouble nanogenerator. If you have two dielectric medium here, physical contact, you have a charge transferred. If you change the gap distance between the two, you have a voltage change or capacitance change. The capacitance change here drives electron flow from one to the other. These are the golden color of the electrode. So this one uses the driving force of triboelectric charge to drive electron flow from one side to the other side. You convert the mechanical energy to electric energy. Okay? Well, then you say, well, how much energy you can transfer? You can make this completely transparent. Then, so inside here is going to displacement current. Outside here is the capacitance current. I'll come to the theory just a second. You can see this. We made a little two materials physical contact, and you can see the light flashes. 80 volts easily. 80 volts easily for this, okay? So this is the first mode. Let's go to theory. Displacement current. So we have two dielectric, and here's the gap. If we make a physical contact, we deliver electrostatic charge from one to the other. And if we more contact, even more charge. So for these three zones here, you can work out the electrostatics here. And you can calculate the displacement current due to the surface polarization density. Surface polarization, that means the polarization due to this, the presence of this electrostatic charge. You can derive the displacement current have two terms. The first term is dz dt. Z is the gap distance between the two medium. dz dt is the speed at which the other contact which. So the speed at which you contact. The faster speed, the better. Okay. The other one is the rate of the surface charge build up. The rate of surface build charge. So that means the rate of the surface charge increases here. And I think the professor Joe's student showed me this morning about they have a titanium oxide, use a breath on that can generate current, which is due to the change of this electrostatic charge density here. Our trouble generator mainly due to this one, because this is a constant, so the speed at which. So this is unified due to piezoelectric effect, power electric effect, or trouble electric effect, as well as electrochemical effect for power generation. Is all goes to displacement current here. So therefore, this is our understanding of how does a displacement current used to be used in the electromagnetic field, now come to the energy field we are interested in. Then the question for us that how much energy you can generate. When I first started work, people don't believe our piezoelectric nanogenerator. The question, is this right? Later on, I say, oh, you're right. Okay, good. But what's the use? And let me show you what we can use for. Second mode is sliding mode. You slide one against the other one. You change the capacitance. You can get the current as well. You can see this. This was done a few years ago by my student here, Guang. And you can see this kind of sliding mode also change the capacitance. You can get a current. So therefore, used to be called change of capacitance, but now is displacement current for this kind of things. Okay. So this is the second mode. What can be used for? We be able to use organic material, make a zigzag shape, contact separation mode. You can put in the shoes like this. You make a power generator here. And you can make this wireless transmit signal many meters away. This is just the beginning. Use organic materials, use the material we are familiar with, use the trouble electric effect we are familiar with to convert the mechanical energy to electric power. What's the advantage of this? I'll come back to that. Let's look at this one. This is, we make a tubular shape. If you put in shoes, shoes can press like that. Does not add any weight, but we make a tubular. This is a little tubular here. The diameter is about 3 millimeter. So the tubular is that which way you squeeze, doesn't matter. So we make the electrode to be a coil shape. You see, there's a coil shape here. So which way you squeeze, it doesn't matter. Isotropic. So in such a case, you can see a person walking does not add any weight, does not have any discomfort. It generates little power. This power reaches a few milliwatts, so it's sufficient for many of those power, the small sensors we are interested in today. All right, interested today. They can be utilized, use small motions for what we are care about in our vibration is the common phenomenon in our daily life. We talk about low frequency vibration. If you're riding a bicycle, we put it on the basket here, and if a student ride a bicycle, you can see this, and then after he or she riding for a small distance, this is temperature sensor, this is humidity sensor, as well as a GPS position system start working. So this can be utilized for solar-powered motion positioning system. Okay, so this is tell you that we can utilize this vibration mode here. If you have equipment, we have a lot of engineering professors here. They work on the instrumentation equipment. Sometimes the operation safety of equipment is a big concern. You can use this one to detect the operation status of equipment, right? Some safety monitoring of equipment. What are the choice materials? If you make any technique, you need specific materials. Specific material. What are specific materials? For example, if you use the solar cell, you need silicon, or recently there's a perovskite solar cell. So the material you cannot choose other material. This is the one you have to choose. If you use LED, you need gallium nitride. There's no other better material for that. But for tribal electricity, the material choice is almost anything. This is the one example. Show you this. This is a silicon-based, rubber-based one. We can make multiple twists. It's still a power generator. We make sheets, put on the arm. You tap in different position of the arm. the corresponding lights flashes. This can be used for security sensor. What do I mean security sensor? For example, robotics. Robotics, if you put a different part of the body, like a human, if I hit my arm to this podium here, I know, oh, yeah, okay, I hit something. Because your nerve is everywhere. However, a robotic would not know that. How do you make a robotics function like us? You could put this on here, and when the robot hits something, there's an electric signal, then say, okay, retract it. You can make this as a complete like a jacket, wear it. So for many safety measurements, you just need a signal so that can make the right action, because there's a lot of hope for this for home care. You don't want to have a machine that in a room you cannot out of control or squeeze something. It's very hard to know the force or weight it is applied, right? So the material choice can be broad. This is reason we did use the polymer based. What kind of polymer? Shape. This is not only shape adaptable but also healable materials. This polymer, when you make a nanogenerator here, use a knife to cut it, then you put it in a furnace, put it together, heat up to about 100 degrees C for 30, 40 minutes. They come together, and it still functions. So therefore, this one is tolerable. You can make a piece, cut, and then you tell a different shape, heat it up, they become the same piece. You can make a 3D shape here. Even use a 3D printer. We have new 3D printer to make this as well. So therefore, the choice of materials is diverse and application is diverse too. This can be also a very important, not only a power source, but a sensor as well, okay? How much power you can generate? We make a board. This board is about 1.5 feet here, and put it on the floor. A person free walking is being lit so many lights. This need at least the output voltage 2,000 volts. And this generates probably around 2 watts of power. That's for many sensors. That's enough. That's enough, right? So this is, if we put the floor, anybody free walking, you'll be able to sense something, send a signal out, okay? So this is the one. For a country like Canada, you have huge land, water surfaces. How can you use the natural wind to monitor something? And we use this ribbon. This ribbon is basically fabric ribbon. You cut the fabric to the stripes, and then you coat the surface with different materials, and you put them together like this, okay? And in the wind blow it is a little power generator. You can be a moisture detector, you can be a humidity detector, you can be a smoke detector, and all this can be function as. So when I talk about this one, is for large area, agricultural, forest, monitoring, this can be utilized for that purposes. So this we can choose the materials we wish, and the cost can be low. The cheapest material we can use is paper. This is 2 pieces of paper. We drew some holes on one paper. The reason because when we apply ultrasonic wave from one side, we can trick one piece of the paper, then can wobbling against the other piece, cause contact separation. Just this, we could generate power. Also, you can see, this is the device, you see? This is the paper-made device here. And that paper have a power output not too large, 0.12 watt per square meter, not too big. But let me see if I can have the voice play out. This is a student. He's talking on the phone. Okay. What this phone, let me shut the, okay. This, we put our generator on the surface of this phone. And this phone, when somebody talks, vibrates. Vibration, be able to charge a capacitor here, and this is the charging curve of the capacitor. Voice power. Voice power. You put this as art on your wall, you're talking, it is recorded. You're talking, recorded. And recently, we have a few professors from Georgia Tech computation science. They are doing microphone research. And use this, make a 3D microphone, make like a sphere or shell, 3D microphone for voice recording. And they find it's very interesting. These people work with Google, and they find this could be very interesting for future other application. Then I don't know about that, okay? So you can know that paper-based. So when you use the paper-based, it can be cheap. Can be diverse, right? So this is the one. Medical. Remember I was talking about you to drive a pacemaker. A few years ago, we used the small rat. The breathing of small rat be able to drive a simulated pacemaker. Simulated pacemaker here. But that time we demonstrated the feasibility utilize this. But it was not good enough. We move on to large animals. This is small and little rat like that. Large animals. And what we utilize is the 50 kilogram pig, okay, for this kind of experiment, because the heart is relatively large. And we recently find if the heart beat once, the power generated be enough to drive the pacemaker twice. Now, I anticipate soon we can reach one, the heart beeping once, the muscle motion drive the pacemaker 10 times. 10 times. We can truly make a self-powered pacemaker. They say, wow, this is still a long way to go. But there's hope for implantable medical devices, and we can store the power, send a signal out, make all this kind of comparison with the ECG signal, etc. We have done a lot of sophisticated work in this regard. So where are the future of pacemakers? According to the prediction of Journal of American Cardiological Journal, they found that, well, the current technology is this. Okay? Then from now on, the future ones will look like this. How can I power this? They call batteryless device. They don't need the battery for that. And I think that use the muscle motion of the breathing can be sufficient to power this kind of device for that. So that's the future. That's their prediction for the future. It can happen many years, not many years, probably a few years from now on to do that, right? So small power for that. For iron research, we collaborate with a Singapore group. They do this the drug injection into ions, and use our traveler nanogenerator here. We can use the motion of a person, the muscle motion here, and this little power be able to stimulate electrochemical process, generate a little gas bubble. And this gas bubble push the pump. The pump push the drug into the sites at which the drug will be delivered. So this is still in the progress, and this team are very excited about that. They want to see the nerve excitation, the stimulation, nerve stimulation, as well as other drug delivery by this technique as well. Okay, so this is the one. We are looking for not only a power generator. We have a lot of faculty students here work on energy storage, very important. We're looking for a system. We have many EE people here. We're not looking for, we need a system. We have sensor, data process, display, wireless transmission. We can build the whole thing in the shoes. Okay, so we are looking for not only a power generation, but a storage. The most important thing is a power management. Power management. Used to be the power management is designed for a fixed frequency like 50 or 60 hertz. But now we have a power generation that is different. For example, our environment field of the irregular energy, people work faster or slower. We can convert this irregular energy into power, but this power is still irregular because it responds to mechanical actions. This is the output. The characteristic of this generator is higher voltage, lower current. We need to lower the voltage, raise the current, so we can effectively charge a storage unit, then regulate it or buffer it for driving all these kind of devices here. Okay, so we have a system, power generations, power management. This needed a lot of circuitry design. We made a lot of progress in this, plus a storage unit. So this is the whole system here. So we try to approach that. So we try to demonstrate in our lab is a power generator, and this is the circuit board, and this regular power be driving this small electronics sustainably. So this is the example show you that we have our people, they have pressed this a little bit, and this is just a demo I show here. This is a power generator here. This is the circuit board we designed, and they bring the voltage down, current up. We have about 65 to 7% efficiency for that part, for the energy management part. And then you can see that after here that there's a car located 30 yards away, then you can see that you can control the lights on and off by this technology. This is a simple demo, but it shows the possibility of self-powered operation. We also integrate solar cell with trouble and generator, simultaneous harvesting mechanical and solar energy. Just like a wearable electronic, we can under the light, we have solar light, right? Photovoltaic. If we have body motion, we have mechanical energy. Can we use both? So we said, yeah, we can make this fabric. This is the power fabric. Simultaneous harvest the solar and the mechanical energy into electric power. And of course, this is not that advanced yet, but just demonstrate, we show this fiber-based solar cell plus fiber-based triboelectric nanogenerator. As you see here, this is the output for the current. The solar part have high current, but low voltage. The triboelectric nanogenerator has a lower current, but high voltage. We can manage both and utilize to drive charge a phone. Okay, you can see during the driving, all this mechanical wind here, they'll be able to drive something. So we call hybrid energy. Utilize whatever is available, whenever it's available. Hybrid energy work here. What droplet? I don't know, but here in some part of the world, it rains a lot. Okay, and if you just solely rely on a solar cell, that part sometimes you're out of luck because it rains a lot. Okay, so what we can do is this: we use the raindrop is naturally charged. When the rain from the sky, even snowflakes is charged. When it fall down, it's charged. So when it hit the surface, it changes the symmetry, electrostatic symmetry between one electrode and the other one. And so when the water level rises, you can further change the symmetry of the electrode. The electron has to flow if you design a circuit like that. Utilize this, you'll be able to convert tiny water drop energy into that. You can. This is the generator here. This is the generator here, and this is the water level wobbling. The wobbling of the water level like that. You can see the light flashes as well here. Okay, and this other one is a shower head, and just shower on top of here. You're gonna see those light flashing as well. Right? Since you use water droplet, some of the power we never utilize for self-monitoring of many things. This is study this liquid at a solid interface interaction. It's very interesting chemistry and physics. And this triboelectricity does occur between liquid and a solid. Most time we look solid and solid. This is liquid and a solid. And if you for Medicare, then you have a microfluidics. If you have a droplet come down, one drop, the other one. This drop contact with the metal electrode, you have a signal here. You count it. How many drops come down? You just count the peaks. Oh, you have this tube here, you have bubbles. If the bubble moves up, the bubble count electrode, you have another signal. You can count how many bubbles goes up. So Rita used a video system. This used the system used the contact electrification between liquid and a solid or air with anything change the symmetry of the equilibrium of electrostatic charge, give you a signal. And you can even use a fully liquid clothes. You can liquid this one, and you can see this this person pressed this water bed, and this just the signal here. I think for sleeping behavior monitoring, for medical care, and other things, you can think about that, right? So this is the portable instrument. A lot of portable instruments need a high voltage power output. Let me give you an example. Mass spectrometer need an ion source. And this ion source is normally driven by a high voltage DC. Then do the analysis. What we did is that the power for drawing the ion source replaced by our trouble generator. And with this one, the total number of charge delivered inside the ion gun here is fixed. So therefore, we be able to achieve the highest mass spectrometric resolution. If you have 100 molecules, we can identify what are these molecules. So for mass spec, we find a way to do that kind of things. And this is the result. I'm not an expert on mass spec, but my colleagues, they are, and they can identify this have a dramatic improvement for mass spec, which is a field very important for chemical and analytical chemical as well biological analysis. Okay. Electron spin make the fibers, nanofibers, use polymer. They normally apply a voltage and a nozzle squeeze out. Here is used to our trouble nanogenerator as high voltage can squeeze this out. You can get this fiber made as well, right? So you don't have to be for that. And recently we have other things done. We use high voltage as well, and some more publication will be like field emission. Also have plasma excitation. Both has been done in our lab on this one. Okay. So what I talk to you now is focus on small energy, smaller scale energy. The question is, can you offer anything for larger scale energy need? So here I have a new idea I want to present to you. Okay. So around the globe, there's huge amount of energy we always waste, rarely use. We only use a very small fraction of that. One of the source energy is the water wave. And in order to harvest water energy, you use the electromagnetic generator like this, and you design here. This design is expensive, engineering difficulty, and low efficiency, plus only work on the shallow waters. If you're deep water, you cannot do that. It's just too expensive to do it. So that's why half this energy used the classic technology become very difficult. How do we do it? How do we do it? When Faraday invented electromagnetic generator, he utilized this kind of equipment. Later on, design more sophisticated one and engineering perfect, make it a perfect power generator. This needed very many years for that. And this is our backbone technology for power. The question is, what are the disadvantages of this? We rarely think about this. What's the disadvantage? Because more than 150 years ago, you don't think about the disadvantage of this one. This is the only choice. You just use it. Use it or leave it. Rather than say, okay, because you don't have two to compare. But now we have two to compare. Which one's better on which are better here. Let's show that. So we made a magnetic generator here. We have a trouble generator here. Same volume, but different weight. And this is heavier because it has magnets. This is lighter because it's used to foils and films here. Okay, let's look at the output. For electromagnetic generator, the output current and the voltage linearly scale with frequency. So both voltage current linear scale. But for the trouble electric nanogenerator, the voltage is constant. The voltage is only related to the degree of the magnitude of the sliding. If you're sliding slower or sliding faster, it doesn't matter. The voltage is fixed. But the current is linear scale with frequency. So the power is a linear frequency dependent relationship. Now this is the key. So let's see how does this impact our future. So we made a rotation-based this electromagnetic generator and rotation-based trouble electric generator. Let's compare. Of course, both are different volume and different weight. Let's disregard that. Let's rotate this one. And this three lights is driven by a trouble generator. As soon as this rotate, these three lights flashing. That means the trouble generator immediately sufficient to power these three. But this three light is powered by this electromagnetic generator. It didn't lit up until the rotation speed reached about 300, 400 rounds per minute. This is how many rounds per minute. And you can see, once the flash here, this starts flashing. And when the speed reach about 350 to 400, this lit up very much. So this tells a difference. This needs a higher frequency to drive. This is just low frequency, be enough to drive that. So that's why at the very beginning, I show you this video, the key difference between the two. Used to be, we must use this one. We use the gear, transformation, all these kind of things, try and make a low frequency rotation to a high frequency rotation in order to utilize it. Now we don't have to do that. This low frequency, be able to drive this directly. That's the key difference between the two. Okay, now, then you see, tubular nanogenerator has a high voltage, low current. High voltage, low current. If you want to charge a battery, we need to lower the voltage, make most of the power to be able to effectively charge the battery. But when you have an electromagnetic generator, you have a low voltage, higher current. If the voltage is too low, those currents are useless. You need to get a threshold above which they can use. So that means the rotation speed has to reach a critical number before the power is utilized. So therefore, you need to raise the voltage because, and then this is going to charge the battery here. So this is the difference in the practice. How can you make the two work complementary? So, in order to apply what we have, this is the electromagnetic generator, we have to make a dam like that, and we have to make a gear shift like that. We cannot utilize the power like this because the potential energy is too small, the impact speed is too low to make this run at high frequency. If we could use this, there are energy everywhere. There are power everywhere. Okay? So now how can we make effective use of this one? So we made this one. Let's say we make a sphere tubular generator. So inside the sphere is a core. If you put this in the water like this, the core, inside core will roll back and forth randomly. So you can see this is rolling back and forth here, and those light flashes here because the power generator can higher voltage, at least 50 to 60 volts can drive this. Now, if you use this one, how about those one? So this is the tubular generator, make a sphere fully encapsulated, put in the water, can drive this. So we have an idea. Let's say, well, we have low vibration frequency, changing environment, wobbling. Can we make a network like this? If we can make a sphere like that, we make a network like this, we could generate quite a lot of power. Okay? Then your question is how much power you can generate. We did a theoretical prediction for that. For this sphere now, we can generate about 2 to 3 milliwatt. Not big, but it's a size about like a tennis ball. Okay. Now, if you make this kind of network here, make a networking 2-dimensional, even 3-dimensional, for the size of 400 kilometer by 400 kilometer size. That's the size of the state of Georgia. 10-meter depth of water for 3D. If each sphere give you 10 milliwatts output, the total power generated from there is 16 terawatt. 60 terawatt is the world total power consumption today. So in probably 15 years later, there'll be double, 30 terawatt. So how big is the state of Georgia compared to the ocean surface of the world? 10,000, 4.3 part of 10,000th. That means 0.04% of the surface area of the ocean. Very low, tiny dot. Okay, but this one, if you work on this one, disregard off the shore, the depth water should work day and night. And it works better in the evening. This is the difference. We hope to have a sustainable energy for the future. But this is the dream, okay? Now we have not done that yet, but we are moving forward. I drive our team to do that. And so what's the key difference? Let's look at the limitation. The limitation is a physics limitation. It's not an engineering limitation. The power output of electromagnetic generator, the voltage is linear square to frequency, the current square to frequency, so the power is square of the frequency. For the trouble electric nanogenerator, the output voltage is constant, The current linear frequency, so the power is linear frequencies. In such a case, experimentally, we have this is the troubled nanogenerator, this is the electromagnetic generator. When the frequency is lower than a certain value, the output voltage is lower, you cannot drive anything. So therefore, at a lower frequency, this is almost cannot be utilized. But ours, just in this region, we have a very good output power. So what's the cutoff point? Roughly about 5 hertz, below which ours have a killer application. So this is a comparison one. Compared to technology, if you have a higher frequency, use the classical electromagnetic generator. If you have a low frequency, use ours. Today, for Internet of Things, for human activity, we all low frequency. We don't have high frequency for that. So both are complements, not one replace the other one. So if you look back, if 100 years ago, when a pioneer designed the power system, this was the only choice. So they have to work on that things. But if many years ago, if we have 2 competing technology, could be this different. Some part can use this, some part can use that. So this was the part I think can be utilized for purposes. This limitation is not an engineer limitation, it's a science limitation. You cannot go beyond that. Go beyond that. Okay, so this is the difference between 2. So we are making progress. I don't have the sophisticated equipment for that. So in our lab, we can make a pool. Okay, so in the pool, our students do this. You see this little device made? You see the light flashes like that? Okay, and we make all this. It works. But of course, we have not made that big 1 kilometer for that. We don't have the resources to do that. We don't have the personnel to do that. But proof of concept, they should work. It's just how do you design this one to achieve the future technology? So I call this blue energy. Why call blue energy? We have enough green energy. We're tired of green energy, right? We want to go blue. Blue water. So blue energy is this one. And hopefully one day we could achieve this one, but of course we have a long way to go. You try to solve one of the most challenging problems in the world. You think you can solve it in 1 year? It won't happen. If that's too good to be true, So we are moving slowly in this regard. I think we have a lot of talented students. When you get this idea, you can move on this one. So I wrote this one we call blue energy dream. The energy we can dreaming, still dreamless now. And if you're dreaming, you can have a better future, all right? Put your action on that. So in our life, we have all kind of low frequency. No high frequency. We have to make a low frequency into high frequency in order to utilize that. That's what we have to do. If we relate to human activity, Internet of Things, all this one is low frequency. We can try to utilize it. So this technology, I think, can be complemented to class technology to utilize somewhere. We need a lot of genius students to think about that in our region. Lastly, nanogenerator is a self-powered active sensor. A lot of sensors we have today is passive. That means that you have power, the sensors. If you no power, sense nothing. A lot of cases like our home security system use that. They constantly have to drive power. If no power, no sensing. So this one, let me show you so we've made a board. There's a board here, and tapping different part of board give you electric signal output. It's a sensor. And different part of triggering here. You can use this for automobile safety. You can put on a carpet in a home, security home, smart home. Here we go for this. This gives you a power source, signal here. Keyboard. We have very many people working on typing. Each one type differently because the way you type different between different letters, different phrases, the way you strike the key is individual dependent. So we put this on a keyboard. Our student type this one, type same phrase. This guy give you this signal, the other will give you this signal, the other give you that signal. Completely different but self-reproducible. And then how can we utilize this to design a smart keyboard? This keyboard identify who is using. Even you know the password. So this guy, let's try again it. The way they type it didn't fit the system, so out of luck. Okay? Out of luck. The guy second guy came in here, type it here, out of luck. Because the electric signal generator has to match the system. I think this can be used for future safety of internet safety as well as the banking system safety, right? Somebody want to get your cash out of that, out of luck, right? This guy, let's see. Okay, he got it working. Recently, we have improvement. We improved this one. Let's say you type a paragraph. Then we derive the features you typing. Derive the features you typing. Then computer will use this feature. If you retype another paragraph, identify is this you typing or not. We will achieve almost 99% accuracy. Let me show you this one. Okay, it's a demo. Okay. Let's show you. We just make a simple pad here. This user one, okay. They made this smart pad here. And type a letter. You see on the top of the screen is A07345. And this uses just one finger typing. And the computer will tell him who is. Hello, Changsheng. Is Wu Changsheng is my student. So the computer will identify who is typing. Second one. The second guy come over. Type the same phrase. Same phrase. They can recognize. Before that, they used the trainer system. Their typing habit already installed. Okay, so only allow the authorized users to get it, not anybody. So you can see this one, and I think when birds try the same word, you can see that. Computer different. This is like the voice recognition. Today we are very powerful voice recognition. But voice recognition was first invented 1982, long time ago. This something could be future too. But start from the small power generation. Google Glass, or we can make this on the rim of the glass, use the blinking of the eye to trigger the switch. And you see the blink of the eye trigger the sensor here, and this glass can be smart, can detect the signal, and the guy you can see, and you can see the light be turned on and off. Okay, I saw a demo a couple of days ago. Was a professor at Georgia Tech. They do this really smart glasses. Use the eye to control the iPhone. I think that would be the future. Besides, I will use the finger to control that. You can do typing too, and typing can be left eye and right eye, 01 or 10. You can do simple this typing here. Okay, so those ones we are working on that. Okay, and bridge. Safety bridge, we can monitor the bridge safety. You can measure the frequency of the bridge. Utilize the vibration bridge. You can store the power and measure the resonance frequency of the bridge, and then send a signal out. By self-power, we sometimes do not mean continue to send things out. Sometimes you don't have the power to do it. But you measure the bridge frequency, and then send a signal. It's called actified mode. Then the sensor can sleep for an hour before the second one. During this 1 hour, the vibration bridge give you power, store it. So self-power means that occasionally, you periodically send a signal out. Does not mean you continuously. Just like your cell phone, if you keep talking for an hour, it's out of power. Just call and in the sleep mode, it's okay. Standby mode, actified mode, standby mode, actified. That's called self-power. So when you think of self-power, you have to think of this one, so it can make it sustainable. Medical, we can put this one on here, measure the pulse of a person, and also we can derive the blood pressure of the person through this kind of sensors. Really type things here, and I think this can be used for medical care for that. And robotics. Robotics is great, but robotics don't know how much the force to grab one thing. So we designed a feedback system on an arm here. And when you hold a cup of water, if this apply too much force, the cup crashes. If you too light, the cup drops. Just have to be right. How right is right? Robotics is very hard to know that. We can build this on our hand to do that kind of things, right? To do things. So have a tremendous application for that things. So summarize for the nanogenerator, we focus 3 applications. Micro nano energy system. This is for very many things we care about, the Internet of Things, and also for large scale energy need. This is a large scope of energy need. Lastly, soft power sensors. There are a lot of things need to be motion sensors, actuation sensors here, which can be used for like automobile, for other security, many other things you need for that. I think this one can be 3 major directions can be used for that. But of course, this is a long dream. We need a long way to go. But at least we have a hope to get there. So, lastly, fundamentally, what's the innovation? The time variation of magnetic field give you the electromagnetic generator, which is using electromagnetic induction, which different from the surface charge polarization density change as a function, the variation, which give you the triboelectric nanogenerator. Use contact electrification, electrical introduction. This one has high voltage, low current. This has high efficiency and low frequency. This one has high current, low voltage, high efficiency and high frequency. Both are complements utilized for different purposes for that. So this is the key difference for that. So looking forward, we always say magnetic field and electric field are equivalent through the Maxwell's equations. The time derivative of magnetic field give you the electromagnetic generator. Now, if you have a surface polarization charge density variation, you can produce piezoelectric generator or triboelectric generator. But inside the triboelectric generator or piezoelectric generator, the dominant transport current is displacement current. Outside on the load is capacitive current. Both meets at the electrode form a loop. Why do we keep calling this nanogenerator? First one, which was named when we used nanowire for this one. Now this one, nanogenerator represent a class generator that utilize displacement current rather than conduction current use electromagnetic generator. They are physically different, represent this branch. So there's a clear difference for that. So we call nanogenerator now have more meaning, more significant meaning than that. So if you look at displacement current, first people use this one, derived electromagnetic wave, which is the foundation of today's communication, wireless, everything. Okay. However, if you add up the time variation of surface polarization density, you get the theory of piezoelectric nanogenerator and the triboelectric nanogenerator, which is the energy for small things, for Internet of Things, for sensors. And I think this field hopefully can grow in the next few years or so, but of course we need some time and a lot of support for that. But we hope our work extend Maxwell's displacement current with the additional term to the field of energy. This is something new. This is a new area which has not been explored at all. So this one I hopefully can in the future develop for them. Okay? I think see the time runs very quickly, but let me go this very quickly. Figure of merits. People can look at our papers. When you do the solar cell, people always talk about efficiency. When you do about thermoelectric, people talk about ZT factor. It's the measurement factor. So what is our factor? We did derive a factor. We use an analogy of these Carnot cycles here. We studied the build-up voltage and total transport charge as a cycle. We find that this loop, the area of this loop represents the total energy generated. If you maximize this loop, it's equivalent to you maximize the Carnot cycle here, you get the very best efficiency. So theoretically, what is the maximum area we could do? So what's the upper limit? So we work on this. We manipulate the system by open circuit and short circuit. We can control the voltage build-up and the charge build-up process so that we can maximize the area of this curve. Theoretically, it is this. So we utilize this one, we derive the equation, we give the figure of merits. Figure of merits have two parts. One is called materials figure of merits, which relate to surface charge density, electrostatic charge density. Structural figure of merits relate to the design of the one. The whole figure of merits is the multiplication of the two, give you the total figure of merits. So this have two parts, is the figure of merits of materials, figure of merits of the structure. We have this online. You can calculate what the figure of merits you got. You can figure merits you can get for different modes. You could do that, right? So many groups start this one. I have this paper from a group here from the mechanical engineering. They do the study. Energy harvesting has every year about 5,000 papers. We invented piezoelectric generator right here and inspired the world effort in this. This is the troubled nanogenerator invented here. And you can see the worldwide, there's a lot of effort being going on. And I hope to see something in Canada. Be something in Canada. There's a map. We need to zoom in, all right? Gonna grow. We need to grow. But I believe it will grow. It will grow because there's a need for that. Okay. And also about 130, 20 units study this. 30 countries, regions, and many authors in this area. So I think it'll grow very fast. Also, the research can cross the board. Anything you do can relate to this kind of thing. For power, for sensors, particularly to current technology need. So I anticipate this can be a fast development in the next few years. Even the cost has started cost. How much the cost compared to nuclear power, have compared to solar power, wind energy, our at the lower end. Our lower end. This is just beginning. This has been around for 50, 100 years. They have been well established. Even solar has been around 70, 80 years. It's not new. It's not new. LED has been invented 60 years ago. It's not new. We just beginning. We still at the low end. I think we can further lower the cost for the commercialization of this one. But this is just my anticipation for that. Even the market, there's a company do market projection. This company, Aditech, they produce for transducers. This have 400 million market. Even for distributed energy, the company called BCC Research, they have this is over 109 billion US dollar for next few years. Huge. If we can a little bit piece of this one, it can be big too. So you read those reports, they predict the future for mobile, distributed energy. Of course, we're not doing this centralized energy for that. So I wrote a book for the troubled nanogenerator. This is the English version, this is the Chinese version, and the student can read this comprehensively and summarize our work until about, I would say 2 years ago. Okay, 2 years ago, okay? So at the very beginning, people don't believe it. People question how far you can go. Look at the Faraday's time. When he was doing this, I bet people don't believe what he can do. So he gives talks, tell them this could be important. This could be interesting. People talk about. I don't think that he will even believe later on develop something like that. Anything at the very beginning looks small, looks not very significant. But give time, give resources, give effort. Particularly, most important people, you have to engage it. If you're just waiting for it, nothing will happen. Nothing will happen. So therefore, when we talk about original research, original idea, need a long time evolution. Sometimes we look for revolution, but revolution has to be built on evolution. If you don't have enough evolution, there's no revolution. So therefore, I think we will persistently pursue this direction. Hopefully, we can solve some of the energy need today we are facing, particularly in a new era of Internet of Things, new era of sensor networks we are interested in, okay? So our research can be summarized by a tree. Today I only talk about the troubled electric nanogenerator for the application around this area. I have not talked about the Piezo Tronics, This is another area we established during the course of our search for micro nano energy, which particularly for LED solar cell tuning use troubled electric as a gating voltage for that, which one we did a lot of work on that, Coupling semiconductor piezoelectric, we call Piezo Tronics. Coupling semiconductor piezoelectric and photoexcitation, we call Piezo Tronics here. Those areas are a rising area, become interesting right now. There's conferences being held worldwide, which is session on that one, which today, due to time limitation, are unable to give you detail for that. But even those introduce new effects. Piezotronic transistors, piezotronic effect, piezophotonic effect, those ones are well received now. I was introduced this concept back in 2007. At the very beginning, also people don't believe it. Okay, but through time, they prove it is there. More importantly, room temperature effect. You don't have to cool down liquid nitrogen to measure room temperature effect. People measure it's there. So one of the German professors, he visited me, said, why didn't I think about this at the beginning? We done piezoelectric for our life. I said, well, I'm very sorry about that. And so sometimes just think a different thing. You look from different angle, you have different understanding. Okay? So this can be very interesting for EE people, particularly for human-machine interfacing in artificial intelligence. This today, we need this kind of things. So lastly, I just briefly introduced the institute I was running, Beijing Institute of Nano Energy, Nanosystems. I was the founding director of the center, start from myself. Slowly, surely. Up to now, we have about 300 people, over 300 people, and we have about, this is local in Beijing, have about $30 million capital equipment for fabrications, and also we have a new campus. This is the new campus, going to be like this, going to be ready by end of this year for moving in. And what do we need? We need the brightest young people to work for us. So I advertise here, if you have interest to go back there to work, contact us. We have the opportunity for you, okay? So at the end, I'd like to thank very many of my people that work with me, support from various sources. Without their support, I cannot do what I do. So come to the end. We mostly talk about the three things today. Is talk about the displacement current. How do the theory evolve to scientifically evolve to a technology? Then it's from technology evolve, how from technology to product. We have some product come out soon, okay? So for solar power system, large-scale blue energy, solar powered sensors, I think those ones will become more and more important. I hope more people, this is a very huge field. We need very many people work on that. We can only do a little bit of that, but we need very many people, young people look at that. And there's a big opportunity to come. And this is, I think this is from a CNN interview I did January 1st, 2013, 5 years ago. At the very beginning was just the one. Yeah. So I'm done my part. You can listen to the CNN broadcast, and then I'll be more than happy to answer your questions. Sorry for running a little longer than I expected. Thank you for giving me the patience. Yeah.